Imagine for a moment the controlled chaos and incredible precision you need for a live sports broadcast. I mean, every millisecond counts, right? Every single pixel is critical.
Yeah, absolutely.
Or picture a massive concert where flawless audio and video need to reach millions, all perfectly synchronized. How do the pros ensure that incredibly high-quality, uncompressed stuff arrives perfectly without miles of tangled, specialized cables or any noticeable lag?
Well, that's the fundamental challenge, isn't it? Traditional broadcast infrastructure, it really struggled with that. The demands of modern media production just kept pushing, and the industry had to rethink everything, find a genuinely revolutionary solution.
And that solution, the foundational answer to delivering that flawless experience, that's what we're diving into today, SMPTE ST 2110.
Exactly.
And this isn't just about moving video around, it's fundamentally breaking down professional media, video, audio, all that crucial extra data into precise independent bits and sending them all over standard IP networks.
Precisely. And our mission in this deep dive, really, is to give you a shortcut to understanding the core of ST 2110. We're going to unpack, how it evolved from older tech.
Right.
Delve into the critical stuff like precision timing, look at how different media types are handled, and highlight the network design practices that actually make it work.
So by the end, you should have the key insights to really get how modern broadcast and AV over IP systems operate.
That's the plan.
Okay, let's unpack this then. To really grasp the power of ST 2110, we kind of need to look at what came before it first. For decades, the backbone of TV stations, broadcast facilities was SDI, right? Serial Digital Interface.
That's right. SDI was the workhorse, the standard for transmitting uncompressed video and audio, mostly over those thick coaxial cables. It was, everywhere because it gave you high-quality, low latency for its time.
But it definitely had some pretty significant pain points. Something those incredibly thick, specialized, and expensive cables.
Oh, absolutely. They weren't cheap, and the distance was limited maybe 30 to 100 meters typically. But the real kicker, the real headache, was that each cable was basically a one-trick pony. Just one video signal and its associated audio per cable. Imagine trying to scale that up for bigger productions, or just adding more cameras.
Yeah, just more cameras.
It quickly became a tangled logistical and financial nightmare.
So the industry clearly needed something better. And before ST 2110, there was this sort of bridge technology, SMPTE 2022-6. What was the basic idea there?
Right, 2022-6. It was an early attempt to get uncompressed HD video over IP networks. It built on RTP, the real-time transport protocol. It was definitely a step forward, getting uncompressed video onto IP.
But if it was a step forward, what was the fundamental flaw? Why wasn't it the final answer?
Well, its main drawback was that it kept that old habit of bundling everything together, video, audio, metadata, into one single monolithic stream, just like SDI did. So while it moved the signal over IP, that rigid structure meant, well, high computational overhead, potential latency issues, and it wasn't really future-proof. You couldn't say independently process or route just the audio without messing with the whole bundle.
Still one big inflexible pipe, basically.
Exactly.
Which brings us to the modern solution, the big leap, SMPTE ST 2110. So after 2022-6 bundled everything, what was the crucial, almost revolutionary difference with ST 2110? What changed the game?
This is the absolute game changer. ST 2110 fundamentally separates video, audio, and all that important ancillary data into individual distinct IP streams.
Ah, okay. Separate streams.
Yes, and this separation gives you incredible flexibility. You can switch, mix, transcode each component independently. It's a highly scalable HD, uncompressed 4K, 8K, HDR, whatever comes next, without needing a complete rip and replace of your infrastructure.
And the robustness, too, must be a huge plus. Like, if you have an issue with an audio stream, it doesn't take down your video feed.
Exactly. Unlike those old bundled systems, it genuinely future-proofs your workflow.
Makes sense.
And this whole separation idea relies heavily on something called Session Description Protocol files, SDP files.
SDP files.
Like blueprints, pretty much. Think of them as the precise blueprints for each separate media stream. They're text-based files, and they're crucial for devices to discover, manage, and dynamically configure streams on the network.
So they tell everything where to find everything else.
Exactly. They provide essential metadata, IP addresses, ports, codec info, and crucially, that precise timing data. It tells every device exactly what to expect from each stream, how to access it, and critically, how to put it all back together perfectly in sync.
Okay, that makes a lot of sense. It's like an orchestra where every instrument has its own sheet music, but there's a master conductor making sure they all play together perfectly.
That's a great analogy.
Which leads us perfectly into the heartbeat of the network, Precision Time Protocol, or PTP, and the ST211010 standard. When we're talking uncompressed video and audio, why is this perfect timing so absolutely non-negotiable?
Well, simply put, without it, you get chaos. Lip sync issues, misaligned graphics, elements just not lining up. It looks completely unprofessional.
Yeah, the dreaded lip flap.
Exactly. For uncompressed, real-time media, perfect synchronization is paramount, down to the nanosecond. And that's precisely where ST211010 comes in, using PTP, specifically the ST2592 profile of PTP.
So PTP is that conductor, making sure everyone's on the exact same beat, down to the tiniest fraction of a second.
Precisely. PTP is the time synchronization protocol that aligns all devices in an IP network, literally to the nanosecond level. It usually references a common, highly accurate source like UTC Coordinated Universal Time or GPS time. This incredible precision is vital for maintaining the integrity of high-res media.
Nanosecond level, it's almost hard to wrap your head around that. We think milliseconds are fast.
It's a different world. Yeah.
And within this PTT system, there's a kind of clock hierarchy. Can you walk us through the different roles these clocks play?
Sure. So at the very top, you have the Grandmaster Clock, or GM. This is the undisputed time authority, the most accurate source on the network.
The boss clock.
Basically, yes. It dictates the rhythm, distributing sync signals to every other device. And it's usually chosen automatically based on its accuracy and stability.
Okay, the ultimate timekeeper. What's next down the chain, helping distribute that time?
Then you often have boundary clocks, or BCs. These act as intermediaries, especially in larger, more complex networks with multiple switches or segments.
Right.
A BC receives time for the Grandmaster or another BC higher up, and then distributes it locally within its own segment or domain. Think of it as a kind of mini GM for its part of the network. It also plays a crucial role in measuring and compensating for latency differences between network segments.
Okay, that makes sense for bigger setups. Now, I've heard about transparent clocks. What's their unique job in this system?
The transparent clock, or TC. This is a really neat innovation for maintaining accuracy. What TCs do is they measure the time it takes for a PTP message to pass through the switch or device itself.
Okay.
And they add this transit time, this residence time, to a special field in the PTP message without actually changing the original timestamp.
So it doesn't mess with the original time signal.
Exactly. Just precisely accounts for the delay introduced by that specific device.
Yeah.
This ensures the end devices get a more accurate picture of the time path, compensating for delays through the network infrastructure without altering the core timing signal flowing from the Grandmaster. Really helps minimize jitter introduced by the network itself.
That's clever, very clever engineering. It keeps that master signal clean across the whole network. And finally, the ordinary clock.
The ordinary clock, or OC, that's the simpler clock you find in the end devices themselves, cameras, microphones, monitors, etc.
The actual gear.
Right. They receive the PTP signal from the network and adjust their own internal clocks to stay synchronized. They're the endpoints, making sure everything aligns based on that master time.
Okay, now bringing it all together, how does this PTP timestamping actually work in practice to keep, say, video and audio perfectly locked?
So this is where the magic happens. Every single ST2110 packet video, audio, data carries a PTP timestamp.
Embedded right in.
Embedded right in. This timestamp represents the exact nanosecond precise moment that packet was created or sampled. When a receiving device gets these packets, maybe from different sources over different network paths.
Right, with different delays.
Exactly. It uses those timestamps. By comparing these universal timestamps, it knows exactly when each piece of video or audio should be played out relative to the others. It can buffer slightly if needed and perfectly align the incoming streams, effectively canceling out network jitter and delay.
Ah, I see.
That ensures perfect lip sync, perfect alignment. That's what ST211010 guarantees.
So the timestamps are like a universal clock reference built right into the data. That is incredibly powerful.
Okay, so now we understand how everything stays in perfect time. Let's look at what that everything actually is in the ST2110 world. How does it handle video specifically?
Okay, video. For pristine, uncompressed video, the main standard is ST211020. This details how to transport uncompressed active video. It supports a huge range of formats, SD, HD, UHD, various frame rates like 24, 30, 60 fps, different color depths, 8, 10, 12-bit chroma subsampling, 4.2.2, 4.4.4, you name it.
The real high-quality stuff.
Exactly. It's designed for zero quality loss, pure, unblemished image transport.
And what about managing the flow of that video data, making sure it arrives smoothly? Is that part of the same timing system?
That's a great question, and it's a separate but related standard, ST211021. This focuses specifically on traffic shaping and delivery timing for video streams.
Traffic shaping, like smoothing out bursts. Precisely. It defines models for how senders should pace the packets to prevent network congestion and ensure they arrive predictably at the receiver. It helps manage buffer sizes and ensures packets arrive in the right sequence for smooth playback. But importantly, 211021 doesn't deal with the overall PTP system timing for synchronization between streams.
Oh, okay.
Its focus is solely on the efficient, well-behaved flow of the video data packets within their own stream. Think of PTP as setting the master tempo for the whole orchestra, and 211021 is like making sure each individual violinist plays their notes smoothly and evenly.
Got it. That clarifies the distinction. Now, what if you just don't have the bandwidth for uncompressed, say, remote production or over a mobile network?
Right. For those situations, there's ST211022. This standard specifies compressed video transport over IP. It's designed for scenarios where bandwidth or latency are tighter constraints. It delivers video using less bandwidth, often with lower latency compared to doing uncompressed transport and then compressing later.
Makes sense to have that option. Okay, moving on to audio. Perfect sound is just as critical. What about uncompressed audio?
For high-quality, uncompressed linear PCM audio, the standard for professional audio, you have ST211030. This is vital for ensuring absolute audio fidelity.
Like CD quality or better, but multi-channel.
Exactly. And importantly, it also mandates support for AE667.
Ah, the audio over IP interoperability standard.
Yes, which is huge.
Yeah.
It ensures that ST211030 audio devices can seamlessly talk to other AES67 compatible systems, like Dante in compatibility mode, Ravenna, and others. A critical requirement here is latency. It needs to be under 1 millisecond in local networks to maintain that perfect sync with video.
1 millisecond. Wow, okay. And what about integrating existing professional audio formats, like the AEC-BU signals common in broadcast?
Yep, there's a standard for that too, ST211031. This specifically covers transporting AE3 audio signals, that's the formal name for ACBU, directly over IP. It lets you bring those signals into an IP workflow without needing external converters, keeping the single path digital.
Very handy for integrating legacy gear. So we've got video, compressed and uncompressed, and audio uncompressed, and AES3. What about all the other bits and pieces that go along with a broadcast? Metadata, subtitles, closed captions, GPI triggers.
All that crucial extra stuff is handled by ST211040. This standard covers the transport of ancillary data, or ANC data. That includes things like metadata, timecode, closed captions, subtitles, aspect ratio information, maybe even custom operational data.
And is that just chucked onto the network randomly?
Absolutely not. Crucially, all this ancillary data is precisely synchronized with the video and audio streams using the same PTP timestamps.
Ah, so the captions line up perfectly with the picture and sound.
Exactly. It's not just sent alongside. It's meticulously timed to match the exact video frame or audio sample it relates to.
Okay, that's a comprehensive family of standards, but having all these separate yet perfectly coordinated streams must put some serious demands on the network itself. Let's talk about designing for performance. Network architecture, best practices.
You're absolutely right. It requires careful network design. And for managing all these devices and streams effectively, there's NMOS, the Network Media Open Specifications.
NMOS. That sounds important for making this manageable.
It is. It's an open standard developed by AMWA, the Advanced Media Workflow Association, and it vastly simplifies discovering, connecting, and managing ST2110 devices and streams on an IP network. It basically provides a common control layer.
What are some of the key parts of NMOS that make life easier?
Well, there are several key specifications, often referred to by their numbers. ISO 4 is for discovery and registration. It lets devices automatically find each other and announce their capabilities.
So things just pop up on the network.
Pretty much, yeah.
Yeah.
Then ISO 5 handles connection management. It defines how you actually make connections, how you route streams from a sender to a receiver. ISO 6 is for network control, managing things like bandwidth allocation and quality of service across the network fabric itself. And ISO 7 deals with event and tally information like signaling which camera is live.
Okay, so it provides that essential control and automation layer on top of the transport.
Exactly. It makes these potentially complex IP media networks far more manageable, interoperable, and easier to scale.
Now, thinking about the physical network layout, the topology, what's the recommended approach for ST2110 and why?
The spine leaf architecture is generally considered ideal for ST2110
Spine leaf, why that one?
because it offers incredibly high bandwidth, consistently low latency, and excellent scalability, all absolutely critical for real-time media transport. It's typically a two-layer system. You have high-capacity spine switches forming the core backbone,
Right.
and these interconnect multiple leaf switches. The leaf switches are where all your end devices, cameras, servers, monitors, etc. actually connect.
And the benefit is?
The key benefit is that any leaf switch is typically only one hop away from any other leaf switch through a spine switch. This creates a very predictable low-latency path between any two devices on the network. It avoids the potential bottlenecks and unpredictable latency of older, multi-tiered hierarchical designs.
Got it. Fast and predictable paths. Now here's something you mentioned earlier, a crucial warning, maybe a real aha moment for people used to traditional IT networking. Link aggregation, LAG, LACP, often used for more bandwidth and redundancy. But for ST2110, it's largely a no-go. Why is that?
Yes, this is a really important point, and it trips up a lot of people. While AG is fantastic in many IT scenarios, it's generally not suitable for core ST2110 traffic flows, especially those involving PTP timing.
Why not? What does it break?
The fundamental problem is that LACP, the protocol used for AG, can introduce variable delays and jitter. It hashes traffic across the multiple physical links in the bundle, and different flows or even packets within the same flow can take slightly different paths with slightly different timings.
Ah, so it messes with that precise, predictable timing ST2110 absolutely relies on.
It's exactly. ST2110 demands deterministic behavior, consistent, predictable performance. LACP, by its very nature of dynamically distributing traffic, undermines this determinism. Even tiny variations or slight packet reordering caused by AG can wreck PTP synchronization and cause noticeable glitches in real-time media.
So the best practice is?
The best practice for critical ST2110 flows is to use single, high-bandwidth network links like 25, 40, 100 GBPs or more, rather than aggregating multiple slower links. This ensures the lowest possible latency, the most precise synchronization, and that vital deterministic behavior.
But you mentioned there are specific places where LH is okay.
Yes, the guidelines are quite specific. For instance, LH is currently not supported or recommended between switches acting as PTP boundary clocks, BC to BC. That connection is too critical for timing distribution integrity. However, EG is often supported and even recommended for connections between a boundary clock switch and the end devices that are just ordinary clocks or timing clocks, BC to OCTC. In that scenario, it can provide useful redundancy and aggregate bandwidth to the endpoints without compromising the core PTP distribution.
Right, so it depends where in the timing chain you are. Very important distinction. Beyond topology and avoiding alibi, what about raw bandwidth needs? You can't just run 4K uncompressed on any old switch, can you?
Absolutely not. The bandwidth requirements are substantial. A single uncompressed HD stream, like 1080p 60, needs about 3 GBPs. A 4K UHD stream at 60 VPs uncompressed can demand up to 12 GBPs, sometimes more, depending on bit depth.
Wow.
So you're immediately looking at needing switches with 25 GBPs, 100 GBPs, or even faster ports for your core infrastructure and connections to high bandwidth devices. And you need the right cabling. Cat6a might handle HD over shorter distances, but for 4K or higher speeds, you're typically looking at Cat8 or more commonly fiber optic cabling.
And a key point about 10 gig ports.
Yes, a critical point. Standard 10 gigabit Ethernet ports cannot handle the jumbo frames typically required to efficiently transport uncompressed 4K video streams, according to ST211020. You really need 25 GBPs or higher interfaces for uncompressed UHD workflows.
Okay, so plan for serious capacity. What about ensuring low latency and quality across the network?
Low latency is obviously paramount, and quality of service, or QoS, is absolutely essential. You need to configure QoS on your switches to prioritize the ST2110 traffic, especially the RTP packets carrying the actual media.
How does QoS do that?
It typically uses markings on the packets, often diffserv code points or DSCP values. You configure the switches to recognize these markings and give the highest priority and lowest possible latency to the critical ST2110 media streams.
So they jump the queue, basically.
Essentially, yes. It ensures that your video and audio packets aren't delayed by less important traffic, like file transfers or management data. QoS also helps manage jitter those variations in packet arrival time and ensures fair bandwidth allocation according to your priorities. It's crucial for smooth, reliable performance.
And finally, VLAN configuration. This can seem complex, but you mentioned some key rules for ST2110.
Yes, getting VLANs right is vital, especially for PTP. There are a few crucial rules. The absolute most important one, PTP traffic, the timing signals, generally must remain untagged on the network, especially on the trunk links between switches involved in the PTP hierarchy.
Untagged. Why?
Because PTP needs the clearest, most direct path. Tagging adds a tiny bit of processing and could potentially interfere with the timing precision or the automatic selection of the Grandmaster clock, the BMCA algorithm. So in multi-switch setups, this usually means your SMPTE devices involved in PTP, like switches acting as BCs or TCs, need to have their management interface or PTP port assigned to the native VLAN, often VLAN 1, because that's typically the untagged VLAN on trunk ports.
Oh, PTP on the native untagged VLAN on trunks.
Right. Now, in a simpler single-switch solution, you might have more flexibility, and the actual media streams, video, audio, data, can often be on different tagged VLANs, separate from management, as long as the PTP stays untagged or correctly configured on its required VLAN path.
So media can be tagged, but PTP needs special handling.
Correct. The key is consistency. You need a consistent VLAN configuration across all your boundary clock and transparent clock switches. And generally, switches in these roles only support running one PTP profile configuration at a time to avoid conflicts.
That's a lot of specific but clearly critical network design points. This naturally leads us to thinking about solutions. How do Netgear switches fit into this demanding ST2110 landscape?
Well, Netgear has made a really strong commitment to the pro AV and broadcast markets, developing switches specifically designed for AV over IP, including ST2110. They focus on three core advantages, making them simple, predictable, and reliable.
Okay, simple. How do they achieve that in what seems like a complex environment?
They have a really user-friendly web interface designed with AV workflows in mind, not just IT. They offer dedicated pro AV design support services. And crucially, their switches often come with pre-configured AV profiles or templates, including ones for ST2110, which can drastically simplify setup. You select the profile, and it applies a lot of the necessary QoS, PTP, and IGMP settings automatically.
That sounds incredibly helpful. What about predictable? How do they ensure that consistent performance?
Predictability comes from robust underlying features designed for media. Things like optimized QoS handling, accurate PTP support, adhering to ST259.2, efficient IGMP Plus for multicast management, and even built-in NMOS support for discovery and connection management on some models. It's all about ensuring those media streams flow smoothly and reliably.
And finally, reliable. What makes them robust for production?
Reliability comes from solid hardware, features like VLANs for network segmentation, strong security features, ACLs, HTTPS, SSH, support for open standards like AES67 for audio interoperability, and integration with monitoring tools like the Netgear Engage controller for keeping an eye on network health. Many models also feature redundant power supply options.
Can you give some examples of where these Netgear switches are being used in the real world for ST2110?
Sure. You see them in small broadcast studios connecting cameras, mics, and monitors. They're used in OB trucks, facilitating streams between the truck and the main broadcast center. In mid-sized studios, they might form the core network connecting cameras, switchers, servers, distributing ST2110 video, audio, and metadata throughout the facility. Even in post-production, they're used for high-speed transfer of ST2110 essence files between editing workstations and shared storage.
Let's maybe spotlight a couple of specific switch series that exemplify this. The M4350 series, for instance.
Yeah, the M4350 series is a great example. They have models designed specifically for these high-bandwidth AV over IP needs. For instance, you might have a model like the M4350-16V4C.
What does that offer?
That one gives you 16 ports running at 25 GBPs using SFP28 slots, plus 4 ports running at 100 GBPs using QSFP28 slots. Huge bandwidth. It offers flexibility with different optical modules, and critically, it has slots for hot swappable redundant power supplies. You can put in different wattage PSUs depending on your needs, ensuring high availability. That's crucial, so a single PSU failure doesn't kill your production.
Definitely need that redundancy. Any other examples? Maybe something with PoE?
Absolutely. There's also a model like the M435040X4C. This one has 40 ports of 10 gigabit, multi-gigabit copper, and importantly, they are PoE++ boarding, meaning they can deliver up to 90 watts of power per port.
90 watts. So you can power cameras, displays.
Exactly. Things like 4K PTZ cameras, high-power Wi-Fi 6060 access points directly from the switch. It simplifies cabling immensely, and it still has those 4 high-speed 100 GBps uplink ports. Like the other M4350s, it also supports redundant, hot swappable power supplies. which is important not just for uptime, but also for increasing the total PoE power budget available across all ports.
Right, you need enough juice for all those devices. Okay, well, we have certainly covered a lot of ground today. Let's try and recap the absolute key takeaways for someone navigating this ST2110 world.
I think at its core, the big takeaway is that ST2110's real power comes from separating media into individual, precisely synchronized streams, video, audio, data, all independent but locked together.
Right, the separation and the sync.
Exactly. And that sync is enabled by the incredible nanosecond accuracy of PTP, specifically the ST2059 profile. Then it's all managed using open standards like NMOS, making it practical. And finally, it absolutely relies on careful network design using the right topology like spine leaf, having enough bandwidth, configuring QoS, and crucially, understanding where not to use things like algae.
It's truly a remarkable shift from the old SDI way of doing things. It feels like it really frees up creative possibilities by removing those old physical cable limitations.
It really does.
And as media production keeps pushing boundaries, higher resolutions, more immersive audio, faster real-time demands, understanding standards like ST2110. Well, it isn't just about the tech specs, is it? It feels like it's about unlocking that next generation of creative potential, transforming what's even possible in live shows, broadcast, and content creation.
I completely agree. It truly is foundational for the future. And it leads to that question, doesn't it? What new frontiers, what completely new kinds of content or experiences will be opened up by this incredibly seamless, flexible, IP-driven approach? Now that we can move and manipulate media essences with such precision, it really challenges us to think differently.
A fascinating thought to end on. We definitely encourage you, the listener, to consider how these principles might apply to your own work or areas of interest, and maybe continue your own deep dive into this really exciting world of AV over IP.